The first concept to analyze on this video is the clean room, and it can be defined as an enclosed area within a manufacturing or research facility that was designed to control air pollutant levels, as well as pressurization, temperature, humidity, and personal access to meet the critical environmental conditions demanded. There are two categories, traditional and modular. While there are benefits and limitations to both, modular clean rooms are becoming increasingly popular for a number of different reasons. The cost of a clean room can have different costs depending on the size, budget, classification, and application of your clean room. Modular construction may be less expensive than traditional construction. However, installing traditional constructions can be a process that takes months to start and finish. By comparison, modular construction is a far simpler process since all the components are already manufactured. Likewise, traditional construction always requires construction professionals. Modular clean rooms, however, can often be built in plant by your own staff with clear instructions provided by the manufacturer. When designing a clean room, it's important to take into account the amount of space its mechanical equipment takes up. In the design stages, keeping flexibility in mind is essential, as this helps with issues of expansion and modification further down the line, as well as with the addition of new equipment and tools as necessary, like room flexibility, airlocks, electrostatic discharge, temperature and humidity, pressurization, and high-efficiency particulate air filters. It's important to mention that clean room environments are strictly controlled using high-efficiency particulate attenuation filters to remove airborne particles, ionizing grids to neutralize static that attracts particles, and heating, ventilating, and air conditioning equipment to exhaust air and particles outside the clean room and maintain positive clean room air pressure.
On the next section, analysis of two components of the motorcycle will be made. These two components are a MTI and a temperature sensor. The first one is the MTI, the possibility to identify with significant accuracy the position of a vehicle in a mapping reference frame for driving directions, and best route analysis is a topic which is attracting a lot of interest from the research and development sector. To reach the objective of accurate vehicle positioning and integrate response events, it is necessary to estimate position, orientation, and velocity of the system with high measurement rates. All MTIs have a powerful multiprocessor core. It processes IMU, magnetometer, and barometer signals with extremely low latencies, and gives several outputs like calibrated 3D linear acceleration, rate of turn, magnetic field, and atmospheric pressure data, along with sensor fusion estimates of roll, pitch, and yaw. The cost of the MTA can range from $20.90 to $26.73, depending on the application. To manufacture this type of MIM, several steps are required. First, there is photolithography. Photolithography transfers copies of a master pattern onto the surface of a substrate of some material, in this case into a silicon wafer. The silicon wafer is covered with silicon dioxide, then a thin layer of an organic polymer is deposited. This organic polymer is called a photoresist. A photomask is then placed in contact with a photoresist-coated surface. The wafer is exposed to the ultraviolet radiation, transferring the pattern on the mask to the photoresist. After the photolithography, it is necessary to use bulk micromachining. Bulk micromachining involves the removal of part of the bulk substrate. It's a subtractive process that uses wet anisotropic etching or a dry etching method to create large bits, groups, and channels. In this case, we are gonna focus on the dry etching method. Dry etching relies on vapor phase or plasma-based methods of etching using suitably reactive gases or vapors, usually at high temperatures. The next process is surface micromachining. Surface micromachining involves processing above the substrate, mainly using it as a foundation layer on which to build. Silicon wafer is added to the substrate in the form of layers of thin films on the surface of the substrate. These layers can either be structural layers or act as spacers. Layers to be removed when they are known as sacrificial layers. This process is used to create the mechanical parts of the MEMS. If the MEMS needs to be larger and have more complex structures, fusion bonding is a good option to achieve these requirements. Fusion bonding allows that micromachine silicon wafers join to other materials. Now let's talk about LIGA. LIGA is an important tooling and replication method for high aspect ratio microstructures. The technique employs X-ray radiation to expose thick acrylic resist of PMMA under a lithography mask. The exposed areas are chemically dissolved, and in areas where the material is removed, metal is electroformed, thereby defining the tooling cell for the succeeding molding step. Finally, the only thing left to do is the assembling and packaging part. Assembling and packaging complex microscopic parts is extremely difficult, as conventional automated assembling and packaging is not suited to such a micro level. To date, many MEMS devices required individual handling. We can see a more general process methods on the next flowchart and some of the characteristics of the MTI that we choose.
The last component is the engine temperature sensor, which accurately measures the engine coolant temperature. The engine temperature sensor changes its resistance with the temperature. Many critical engine functions such as selection of air-fuel ratio, fuel injection timing, and ignition time depend on the engine's temperature. This is because a cold engine requires a rich air-fuel mixture, whereas the engine running at an optimum operating temperature requires a lean mixture. Also, we can say that a coolant sensor is similar to a thermistor, based on the working principle that change in an electrical resistance will be the direct product of a change in the temperature of a wire carrying current. The next figure illustrates the main circuitry of the coolant temperature sensor. With a coolant temperature sensor, the fuel sensor is located in a coolant passage that sits before a thermostat and is connected to the engine control and monitoring unit. Measuring the change in resistance is one method of identifying the specificity of a coolant temperature sensor. It is also possible to measure the voltage drop across sensor terminals while running the engine. As can be seen in the table, we can estimate the temperature through the voltage. Another important feature is the cost, which is around $25. The first thing to do to manufacture an IC is to cut off a round wafer from a cylindrical ingot of silicon using a precise cutting machine called a wafer slicer. Then the surfaces of the wafer are coated with a layer of silicon dioxide to prevent any oxidation of the silicon. The next process is masking. The design of each circuit is prepared on a computer-aided drafting machine, and the image is made into a mask which will be optically reduced and transferred to the surface of the wafer. The mask is opaque in certain areas and clear in others. It has the images for all the several hundred integrated circuits to be formed on the wafer. A drop of photoresist material is placed in the center of the silicon wafer. The coated wafer is then placed under the first layer mask and irradiated with light. The mask is removed and portions of the photoresist are dissolved. If a positive photoresist was used, then the areas that were irradiated will be dissolved. If a negative photoresist was used, then the areas that were irradiated will remain. After the masking process, a doping process is used. There are two different doping methods. The first one is atomic diffusion. In this method, a batch of wafers are placed in an oven. The wafers are heated and the dopant chemical is carried in on an inert gas. As the dopant and gas pass over the wafers, the dopant is deposited on the hot surface left exposed by the masking process. The second process is ion implantation. In this method, a dopant gas like phosphine or boron trichloride is ionized to provide a beam of high energy dopant ions which are fired at a specific region of the wafer. The process of masking and etching or doping is repeated for each successive layer depending on the doping process used until all the integrated circuit chips are complete. Finally, those ICs that fail the electrical test are discarded. The good IC are individually bonded into the mounting package and the thin wire leads are connected by either ultrasonic bonding or thermocompression. The completed integrated circuits are sealed in anti-static plastic bags to store or ship to the end user. On the next section, we can see the flow chart of the process that we just explained.